in an experiment.
We don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, taking antimatter on a road trip
and predicting what researchers might see if two black holes have a near miss. I'm Shamini Bundell.
And I'm Benjamin Thompson. First up on the show this week, a team of researchers want to take antimatter out of the lab and onto the road, and they think they have a way to do it. Now, for each type of matter particle, there's an equivalent antimatter particle, a mirror image with an opposite charge. The positively charged proton has the negatively charged antiproton. The electron has the positron, and so on. Physicists think that antimatter and matter were created in equal amounts during the Big Bang, but now the universe seems to be overwhelmingly made of regular matter. And why this is a puzzle. To try and solve it, researchers are keen to study antimatter, but it's difficult to create and extremely short-lived because it instantly annihilates on contact with regular matter. There are places antimatter can be made and stored, like at CERN, Europe's particle physics laboratory, outside of Geneva in Switzerland, which has an antimatter factory that can make antiprotons. But scientists would love to be able to take the antimatter particles to other facilities, to probe them with different equipment. This is easier said than done, though, because of the whole antimatter being annihilated as soon as it touches matter thing. To overcome this, researchers are looking for ways to safely transport antimatter particles. And this week, Nature has a paper detailing one of them, which could ultimately be used to shuttle antiprotons from CERN to other labs on the back of a truck. One of the team behind the work is Christian Smorer from Heinrich Heine Universität Düsseldorf in Germany. I gave him a call and he explained a bit more about CERN's antimatter factory.
So CERN has a lot of accelerators, and the infrastructure is there to provide a high energy proton beam, and you can shoot this on a metal foil, and then you make protons and antiprotons, and we collect the antiprotons in an accelerator ring, and then we slow them down and put them into a trap. And that's a quite unique way to study it, because you can maintain it for a long time, and you can take your time to precisely determine the properties of the antiprotons in your trap.
But I guess lots of researchers working in different places would love to get their hands on antiprotons. And that's where you come in then. And you've shown in your paper in Nature a way that could be used to store and transport antimatter. But it has to be said, though, that in this work, you've demonstrated this setup using protons rather than antiprotons. So you're using matter rather than antimatter.
Exactly. But we have constructed a system that is supposed to transport antiprotons. So we know the procedure how to get antiprotons into our trap, but that would have required us to do like half a year of additional work before actually testing the transport.
And essentially what you demonstrate is a portable trap consisting of a very cold bottle that contains a really strong vacuum in it. What else is in the setup?
So you have to prevent the antiprotons to touch any walls. So if you have a charged particle like the antiproton, it's interacting with magnetic and electric fields. And there are a few configurations that you can use to hold them really in one place. We call that a panning trap, and it has a magnetic field. So the antiprotons circle around the magnetic field lines. And then you add an electric field that's pointing towards the center. And then you have a confinement of the antiproton in all three dimensions.
And this is a smaller version of a trap comparable to the trap in the antimatter factory. How big are we talking?
In the antimatter factory, we have a stationary experiment that is I would say, about a factor 3 larger in footprint. And we have made some effort to make this system as small as possible. We build it that it fits through a regular door. You could even take it home with you if you want. You should check though that the floor holds, so it still weighs about 900 kilograms, so it's a bit heavy.
Well, let's talk about a central part of the experiment. So you built this trap then, and in this work you've pumped about 100 protons, not antiprotons, 100 protons into the bottle to test whether you could ultimately get antimatter on the road. And you put your setup then on the back of a van and essentially drove it around CERN. And this experiment lasted for about 4 hours.
Exactly. So our trap has what we call an autonomous operation mode. So essentially you can cut the electric power, and then we have some battery units in our transportable trap that manage to hold the particles in position, and you have some monitoring system that you can observe that they are still there. And we have a liquid helium tank inside, and it stays cold for about 4 hours. That's the time we have to put the trap into position in another place and start it up again.
So you disconnected it from the main factory then, put it on the back of this van and set off around CERN. Now you were in this van, Christian, right? You actually took part in this trip.
Yes. So there was Jean-Luc, the driver, and myself in the truck. And we had a couple of people following us with cars. Our trap has a router installed, so people that are close by can watch with their laptops and phones what's happening.
And in my head, I see this as like a heist movie. Like you've put the treasure in the back of the truck and you've put your foot down and absolutely burnt rubber out of the factory. Is that what it was like?
No, we very carefully left.
And how long did you drive around this loop of CERN then?
The actual trip on the truck was just 15 minutes. What takes the longest time is actually to crane the thing out from your experiment zone onto the truck. This procedure takes about an hour one way.
And then an hour on the way back when you return as well to plug it all back in.
Yeah, exactly.
And did the protons that you put into your trap, did they survive the trip?
Yes. So 105 particles were in our trap at the start. And when we returned, we had the same amount. And that's fantastic.
But of course, your ultimate aim is to move antiprotons, the complete reverse. Will retuning your equipment be a relatively straightforward process, or are there other things you need to consider to move from proton to antiproton?
What you do in the end with a transportable trap that we have is you just switch the electric potential from negative to positive, and then you attract the antiprotons instead of the protons. So this part of the equipment that we tested is in principle very easy to adjust for antiprotons. We want to make the antiproton transport this year, and we are currently working on our trap system to install a few more monitors. Once that's ready, we will go back with our system to CERN and see that we catch the antiprotons.
And putting them in is one thing. What about getting them out again? Is that something that's going to be straightforward?
Getting them out is straightforward if you don't care where they are going. But of course, what we want to do later is to make a transfer of the antiprotons into a precision spectroscopy system. So what we need to do is construct a beamline that can make the transfer without losses.
So ultimately then, you're looking for a full system of load the equipment, drive it somewhere else, then unload it. That would be the full system.
Exactly.
And your paper's out now demonstrating what you've done. What does this work not achieve?
Let's say it's the first trip that we managed with the system. We want, of course, later to be able, for example, to transport it over longer distances. And then if you have a time limit of 4 hours, you can't get where you want. So we will need to upgrade our system. But what we can already do is we can supply labs that are at CERN in other buildings where you are just further away from the accelerator and you have less noise and you can make there better measurements.
And Christian, you're based in Germany. Obviously, you've worked at CERN as well. I guess you're looking to take the antiprotons to your university. What sort of distance is that? And will that be a bit of a road trip for the future?
Yes, something like 700 kilometers would be the shortest route, but that's still under discussion how exactly to get here to Düsseldorf. You have, of course, to deal with the public regulations for transporting your equipment on the road while it's in operation, and there's no legislation, let's say, for the antimatter transport. And that's something we need to discuss with the authorities and see where it's first possible to transport the antiprotons on the road.
And is there any risk to doing this at all?
I think the most dangerous thing is that there's a truck driving around. If you get hit by the truck, you have an accident. But other than this, the antimatter is not dangerous at all. The amount that we are transporting is so small. Let's say it's 100 antiprotons. So if you eat something like 10 bananas, you get a higher radioactive dose than standing next to our antimatter trap while it's switched off. So no holes in the highway, nothing like that.
Christian Smorer there. To read his paper, look out for a link in the show notes.
Coming up, a quick way to work out how two black holes might interact if they sped past each other. Right now, though, it's time for the research highlights with Dan Fox.
A tradition of female diving on the South Korean island of Jeju might have shaped the genomes of the island's population and the physiology of the divers themselves. The Haenyeo, which means women of the sea, have been diving for seafood for centuries. They dive year-round without breathing apparatus, even while heavily pregnant. To understand how these divers cope with their lifestyle, researchers recruited 30 Haenyeo from Jeju, along with 30 non-Haenyeo island residents and 31 people from Seoul. The team found that a gene variant associated with reduced blood pressure is more common in people from Jeju, regardless of whether they are divers. They also identified variants in genes linked to red blood cell count, which is related to oxygen carrying capacity, and pain tolerance, which could influence the ability to withstand cold water. Take a deep dive into that research in Cell Reports. Scientists have described a rare poison dart frog in a remote river basin in the Amazon in western Brazil that appears to be monogamous. The frog sports metallic copper legs with dark crimson spots and a back covered in iridescent green stripes, and they're difficult to detect, measuring just 1.5 to 2 centimeters long and with calls that do not carry far. They lay eggs on a species of native banana plant in tiny pools of water that collect where the leaves join the stem. When observed, the animals were paired up, suggesting they are monogamous, something extremely unusual in frog species. The researchers hope that this finding will encourage more efforts to survey the area. You don't have to look hard to find that research. It's published in Zoo Keys.
Next up, physicists have mathematically tackled a key problem in physics, understanding how two massive bodies interact, a result which could help with future detections of gravitational waves. Here's reporter Nick Petrich-Howe with the story.
How different objects gravitationally interact in space has been a head-scratcher for scientists since Isaac Newton.
We studied one of the most fundamental problems of physics, namely the gravitational two-body problem.
This is Jan Plewka, one of the team behind a Nature paper on this problem.
So we asked the question, what happens when two black holes fly past each other? Can we predict the emitted radiation in gravitational waves that comes out? And we're able to push this to a new level of accuracy in the prediction, really extending the state of the art of the field profoundly, I would say.
With this work, the team have been able to predict how two black holes flying past each other interact mathematically.
And that is actually one of the most fundamental problems in physics you could imagine. So the situation is simply that we take, just empty universe and just put two masses in and just ask for questions, how do they interact with each other? So they have initial velocities, a certain distance, fly towards each other, and due to the gravitational force, their trajectories are deflected. And the task is to predict exactly the trajectories, or the question, how many energy they lose through emission of gravitational waves in that process.
Understanding this emission of gravitational wave energy will be key for future gravitational wave hunters. When gravitational waves are detected, the signals are incredibly noisy. So having some sense of what a signal might look like can help you spot them and determine what they were caused by. But the problem itself is notoriously difficult. When two bodies are massive and close enough that their interactions lead to the emission of gravitational waves, it no longer has an exact solution. So typically physicists will have an educated guess about the trajectories of such objects and then use intense computational power to refine these guesses into usable simulations. This process is slow and expensive, so Jan and the team decided to take a different tack. They wanted to create a formula that people can use to work this out in a much more straightforward way. To do this, they looked from the huge scale of black holes down to the tiny scale of particle physics. You see, particle physics already has a lot of calculations to understand how two particles interact. So Jan and the team thought that they could treat their black holes like particles and apply some of those existing ideas here.
This is sort of the universality of physics, or theoretical physics specifically, because as long as these black holes are well separated, we actually approximate them as point particles. And that's why there is no big difference between describing black holes or protons, as long as all we have to do is we change the interaction force between these two objects.
In this case, rather than looking at how two protons might change their trajectory as they pass close to one another by emitting photons, for instance, a process known as scattering, the team looked at how one black hole may change its trajectory as it passes close to another, emitting gravitational waves instead.
So, in a nutshell, instead of scattering protons, which is done at CERN, we now scatter black holes. As we're theorists, we can do that easily without building a machine. But sort of the same techniques that apply for the scattering of protons can be used to analyze this process here for scattering of black holes.
The maths of how this was all done is pretty complicated. But in essence, the team used a mathematical technique called perturbation. Here you have a rough approximation which you progressively refine. To do this, you add new mathematical terms to improve the precision of the result. Here they did it for the strength of the gravitational interaction, which then ultimately allowed them to get a prediction of how the black hole's momentum and trajectories will change. By doing this, Jan and the team have worked out, with a higher level of precision than ever before, a prediction of how two black holes of differing size would interact as they pass close by one another. Importantly, they could also show what the gravitational waves this interaction would emit would look like. Doing this took a lot of computing power, but now it's done, it's fairly simple for anyone else to use.
So at the end of the day, we have a huge formula which gives you the scattering angle of these two objects, and it's a formula where you can plug in the masses, the initial velocities, and the initial separations of the two objects, of the two black holes, and you get a result. It's one formula, it's huge, you have to download it, you couldn't write it on a blackboard, but we have it. We have a formula where you can always plug it in, and now it takes a second or so to evaluate it.
This is much quicker than the more conventional method of using intense computational simulations of how the black holes interact. And it may also be useful for the next generation of gravitational wave detectors.
It's key actually for the so-called third generation of gravitational wave detectors, which are being planned now, and they're scheduled to go online in the 2030s. And they will have higher sensitivity, and that's why we need these high precision predictions that we are now computing.
The formula that Jan and the team calculated won't work for everything. This specifically looks at the situation of two black holes passing by one another. Whereas if you've heard of gravitational waves, you'll probably know that so far these have been detected from things like black hole mergers, where black holes circle each other for a long time before eventually colliding. Jan does think that someday formulas like his could even capture these events though. One other aspect of the work that may prick up the ears of physicists is something that came out while Jan and the team were working out their solutions. In there were complex geometrical objects called Calabi-Yau manifolds. These are odd objects that are used by string theorists to accommodate the extra dimensions that string theory implies exist. These Calabi-Yau manifolds were initially proposed about 70 years ago, but it was unclear what they could be used for. Now, they have popped up in the description of the gravitational waves, showing how mathematics proposed years ago can come round to describe physics people couldn't have imagined at the time.
And they have been studied intensively in math, but also in physics, because they are used in string theory to compactify the 10 space-time dimensions that you have in string theory down to 4. So these 6 extra dimensions are Calabi-Yau manifolds. So that's why they have been also studied there intensively. And amusingly, they now appear in gravity, but in classical gravity.
For now, the team are looking to increase the generalizability of their formula. At the moment, it assumes that the black holes have different masses. If they have the same mass, the problem becomes even more complicated. But the team are hopeful that they'll soon work out a solution for that as well.
If they are really of the same mass, there is one term missing which we have not computed, because the problem is even more complicated. And this is what we're working on right now intensively. And we hope to report by the end of the year or next year on then the final result.
That was Jan Plewka from Humboldt University Berlin in Germany. For more on that story, check out the show notes for some links.
Finally on the show, it's time for the briefing chat, where we discuss a couple of articles that have been highlighted in the Nature briefing. Shamini, why don't you go first this week? What have you been reading about?
So I've been reading this article in Nature about scientists turning lead into gold.
Finally.
Well, it's what we've all been waiting for, isn't it? It's nuclear physics, in case you couldn't guess. It's all about, turning the atoms of one element into the atoms of another element. And the way that we do that is generally smashing things together and knocking bits off. It's all about how many protons, how many neutrons. Of course, all the things that the ancient alchemists didn't know when they were trying to use chemistry to transmute base metals.
And, well, a lot of our show has been about smashing things into other things, so I'm guessing this involves some particle acceleration.
It's the Large Hadron Collider. Yes, exactly, a particle accelerator. Let's get particles up to only a fraction off the speed of light. And when they interact with each other, strange things happen. And in this case, we've got lead ions, and they're not actually smashing into each other to make the gold. They're going just past each other. And there's this effect that happens where the intense electromagnetic field around the ion creates this pulse of energy in the form of photons. And the photons basically trigger an oncoming lead nucleus to eject 3 protons. Lead has 3 protons more on the periodic table than gold does. So if you take 3 protons and a neutron, in this case, away from lead, you get a gold nucleus.
Right, so by knocking these protons out, you get transmuting, I suppose, from one to the other.
Yeah, and it's quite funny, actually, that you can turn lead into gold because they're not that far away from each other on the periodic table, which obviously the ancient alchemists didn't know that. They wanted to turn the cheap metal into the expensive metal, which you'll be shocked to hear is not the main aim of the physicists at the LHC. This was not their plan for getting rich quick, but it was a plan for better understanding how the photons that are created here, can then change nuclei as they have done. And this could actually help the LHC and how it works, controlling beam quality and stability and things, so improving the LHC's performance.
But let's cut to the chase, though, Shamini. Is this a way that we can make gold? I'm sure running a particle accelerator to run a few ions next to each other probably isn't the most cost effective.
Firstly, if it doesn't create a lot of gold, they estimate that between 2015 and 2018, collisions that were going on at the LHC would have created 86 billion gold nuclei.
Wow.
Yeah, it's 29 trillionths of a gram. And the gold doesn't last. I think that's the key thing here. The gold doesn't stick around. So we've got these like massively fast, unstable gold atoms, and they will either then smash into the sides of the experiment or break apart, turning into other things. So they probably only existed for around a microsecond.
Well, that's disappointing. But as I say, the theme of this show this week seems to be stuff smashing into other stuff and then potentially being destroyed.
Exactly. And it's interesting to be able to really understand what's going on there. And this turning lead into gold, this isn't the first time that lead has been turned into gold in a particle accelerator, actually. And every time lead beams collide at the Large Hadron Collider, gold is being made, along with thallium and mercury, who are also in a similar place in the periodic table. So it depends how many protons you knock out. But all these things are being made. But in this particular case, they've set up this experiment with a detector specifically to spot this happening, analyse the signature of gold production, they've said, and thus have really good observations of, you know, how much gold is being created and exactly what's going on in there.
Well, a story that's certainly worth its weight in gold there, Chamonix, and we'll put a link to it in the show notes, of course. But let's move on to the story that I've been reading about this week. And in fact, this morning I was outside my flat and there's some wisteria plants out there. They smell absolutely gorgeous. The bees love them. And this story that I've been reading about in Nature is based on a science paper, and it's about the smell of plants. Now, smelling sweet isn't the only way to attract pollinators. This one relates to how plants like the charmingly named skunk cabbage get their smells.
Oh, so I know that one of these famous rarely flowering plants, and it smells of like rotting meat or something, and that's supposed to be to attract the pollinators like flies and things like that would otherwise be attracted to rotting meat. Is it something like that? Skunk cabbage.
Absolutely right. So they're the corpse flowers, and we'll get to them in a little bit. Now, you're right. These things do smell obnoxious, maybe noxious, I suppose. And yeah, they can smell of rotting meat, they can smell of feces, but yeah, irresistible to beetles and flies. But how plants make this smell has been of interest to scientists. And in this case, a researcher was looking at a group of plants called Asarum, right? They're quite a diverse group of plants. And this work was surveying Asarum plants in Japan. And the researcher in question noticed that some of them smell of rotting meat. So to learn about how plants make these stinky compounds, the team behind this work catalogued them and looked at the differences in genes and enzymes between the stinky and non-stinky Asarum species, okay?
That's got to be some dedication to science. You find like a horrible smelling plant and you're like, I should investigate this further. I should investigate this smell.
That's why we love science, right? Clothes pegs on the nose, I'm sure. And what they found was they pinpointed a class of enzymes called disulfide synthases, which convert certain sulfur-containing molecules into the compounds responsible for the smell.
Right.
And this is in the Asarum, but of course they looked a bit wider and they found that similar enzymes had evolved independently in two other plant genera, and one of which the skunk cabbage is part of. And it turns out that really quite a small change of just 3 amino acids could change an enzyme common in plants into a disulfide synthase that could make the smell.
Oh, so it's essentially adapted from a enzyme that already exists there, which is why it's been able to evolve independently in these different plant species.
Yeah, that's right. And there's lots to understand here because you talked about the corpse flowers, right? These enormous flowers that smell like rotting flesh. They don't have disulfide synthases.
It's a twist.
Yeah, so there's lots to learn about stinky plants, right? So species in one genus apparently repeatedly evolved the ability to smell terrible over 7 million years, which seems like a long time, but in evolutionary terms, that is an absolute snip. And the researchers hope that understanding this mechanism, for some plants at least, will feed into ongoing studies of how various malodorous compounds can be made. And the way it's done, right? Flowers might emit different compounds at different times. Maybe one that smells terrible to attract pollinators, and then release another one to say, off you go, please leave, and head off to another plant to pollinate flowers there.
Malodorous compounds, there we go, a branch of science I didn't know existed.
And there's absolutely loads more of them apparently as well. Flowers have been discovered that seem to mimic the odour of insect blood, so to attract a certain predator into the flower. Some smell like rancid cheese. I mean, my goodness.
It's very specific.
And there's a great quote in this article from someone not involved in the research, and it is, "One recent realisation has been that stinky flowers are more complicated than we thought they were. There is still a lot of discovery to be made."
Isn't there always? Well, I'll leave the stinky science to those scientists there, but thank you, Ben, for telling us about that and not bringing an example into the studio. And yeah, we will stick links to those articles we've mentioned, and also you can sign up to the Nature Briefing. We'll put a link to that and get more of those kinds of excitingly smelly stories directly into your inbox.
And that's all for this week. If you want to keep in touch, of course, you can follow us on X or Blue Sky, or you can send an email to podcast@nature.com. I'm Benjamin Thompson.
And I'm Shamini Bundell. Thanks for listening.